In this section, we're going to be taking a look at how to graph polynomial functions. And the first thing we're going to start out with is something called multiplicity. And multiplicity is going to take a look at our intersections with the x-axis and how the graph intersects the x-axis. So if we look at the first set of graphs right here, the first one is y equals x cubed. Y equals x to the first power. So we have a parent function, y equals x graph. Then we have x minus 2 raised to the first power, which is a shift to the right 2 units. So it's the same graph, just shifted to the right 2 units. And then we have x plus 3 raised to the first power, which transformation-wise, this is a shift to the left 3 units. Now what all these equations or functions have in common is that the exponent on these is a 1. Now notice the zeros on these polynomials. The zeros are where your graph intersects the x-axis. Now if you look at how the graph behaves at that intersection, our graph is just simply going straight through that intersection point. All right, so that's what our graphs are doing. So when it says compare the way the graphs cross the x-axis, we just say the graph goes straight through the zero. All right, so now the second set of graphs that we have here, we have y equals x squared, which is just our parabola parent function. Then we have x minus 3 squared, which is a parabola once again, but shifted to the right 3 units. Then we have x plus 1 raised to the 4th power and x minus 1 raised to the 6th power. Now if you just visually look at the difference between these graphs, right here you can see that when you start increasing your exponent larger than a 2, that the bottoms of these curves start getting a little bit more flat, and you can see that the steepness of the curve increases. So these curves become much more steep when that exponent is increased. So what do these exponents have in common? They are all even values. We got squareds, we got 4th power, and we got 6th power. These are all even exponents. Now notice the zeros. Look at the zeros of the polynomial and compare the way that the graphs cross the x-axis or intersect with the x-axis. At each of these zeros, when you have a curve that touches a line at one point, they are said to be tangent. So that's what's happening on each of these graphs. The curve is tangent, which pulls out a geometry term out of your past. So the curve is tangent to the x-axis at the 0. So just a quick review, when we had an exponent of 1, the graphs went straight through the x-axis. When we have exponents that are even numbers, the graph is tangent to the x-axis. So what do all these have in common? Well, if you look at your exponents, we have a 3, a 3, a 5, and a 5. So all of these exponents are odd. Now look at the way that the graphs intersect the x-axis. Here, 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 and here. If you'll notice the curvature in your graph, whenever you have a graph that is curved down like this is called concave down. And when you have a curve that's like this, that is called concave up. So if you look at our graph here on the left side of that 0, the graph is concave down, and then on the right side the graph is concave up. Same thing here on the next one. It's concave down on the left side, concave up on the right. And then on these graphs, the same situation occurs. So what happens is when you have an exponent that is an odd exponent, you're going to have a change in concavity of your graph at the 0. Here you're changing from concave down to concave up. So there is a change in the concavity at the 0. All right, so in summary, if the binomial in the parentheses has a 1 for an exponent, then the graph will cross the x-axis by just going straight through the x-axis. Okay. If the binomial in the parentheses has an even number for an exponent, then the graph is going to be tangent to the x-axis. So it either comes from above and touches the x-axis at one point, or it might come from below and touch the x-axis at one point. But it's going to be tangent to the x-axis. It does not actually go through it. If the binomial in the parentheses has an odd number for an exponent, but the odd number is not 1, because when it is 1, it does something different. So have an odd exponent other than 1, then the graph will cross the x-axis like this. This is where it does that change in concavity. So if it intersects here, it might come from below, concave down, and then concave up, or it might come from above where it's concave down and then, concave up and then concave down. So it could go either direction like that. But you're going to have that change in direction. So what would be different if there is a negative sign in front of the parentheses? Well, when you put a negative in front of your parentheses, it does not matter which function it is, that is going to cause a reflection over the x-axis. So what do we notice about the end behavior? Okay, the end behavior of the graphs with the even exponents. Let's go back to the even graphs. Here we had some graphs that all had even exponents. End behavior means what happens as the graph moves to the left and as the graph moves to the right. Well, as this graph moves to the left, your function is going up. And as you move to the right, your graph is also moving up. That happens on all of these that have an even exponent. Doesn't matter what the exponent is as long as it's an even number. Might be a 2, might be a 4, might be a 6, might be a 28. We don't know. But if you have an even exponent, that means your graph is going to be moving up to the left and up to the right. Now, keep in mind that if you have a negative coefficient, that means that everything reflects over the x-axis. So if you have an even exponent but a negative coefficient, instead of going up to the left and up to the right, you would go down to the left and down to the right. All right, so now let's look at the end behavior of the graphs with the odd exponents. All right, so here we had odd exponents. We have a third power, we have a fifth power. As you move to the left, the graph is going down forever. And as you move to the right, your graph is going up. And that happens on all of these. Down to the left, up to the right. Down to the left, up to the right. Okay. So that's what we can fill in right here. It's going to go down to the left and up to the right. And once again, if you have a negative in front of the parentheses, this is going to be reflection over the x-axis, which means it would do the opposite. It would go up to the left and down to the right. All right, so the next thing we're going to be looking at in order to be able to graph our polynomials is going to be the zeros of the polynomial. Zeros are going to be your x-intercepts. And when a function has an x-intercept, the y value is always 0. So what we need to determine is, in this polynomial here, what would x need to be in order to make the function 0? Well, to make the function 0, all we would need is for each parenthesis to be a 0. So the x value that would make this parenthesis 0 is -2. The x value that would make this parenthesis equal to 0 is +3. And the x value that would make this parenthesis 0 would be -1/2. So those are your zeros. And what that means, that is where those that equation is going to cross or intersect with the x-axis. So now let's identify the end behavior from what happens with our leading term. The leading term, which is your largest term in your polynomial, is going to decide your end behavior. If your leading term has an exponent that is an odd number and the coefficient is positive, which means it's greater than 0, then the graph is going to go down to the left and up to the right, just like we mentioned earlier. All of this is based only off of that leading term. It does not matter what the rest of the polynomial is doing, only that leading term. Now, if you notice these, here's your leading term, here's your leading term, and your leading term. It does not matter what the rest of this function is doing. This one has an exponent of 1. It's an odd, and there's a negative in front of the for the coefficient, which means you're going to go up to the left and down to the right. This also is odd with a negative. You can see this one goes up to the left, down to the right. Odd with a negative, up to the left, down to the right. Same thing. It does not matter what happens after that leading term, it's still going to do the same thing. Now on this one, all of these exponents are even exponents. As we mentioned before, if the leading term has an exponent that is an even number, then you are going to either be going up on both sides or down on both sides. Now, if your coefficient is positive, that means you're going to be going up on both sides, up to the left and up to the right. And these are just 3 examples of equations that show that. We don't need any of that information there. All that we're concerned about is the leading coefficient. Now, all of these have a leading term that is even. However, they are also negative. So we have a negative here, and a negative here. What that does is it makes your graphs go down on the left and down on the right. All right, so let's now take a look at how do we put all this information together to be able to sketch a graph of our polynomials. Now, this problem right here is in factored form. If I was to multiply this out, and I multiplied x plus 3 times x plus 3, because it's squared, times x minus 1 times x minus 1 times x minus 1, because it's cubed, you would be multiplying 5 x's together for your first term. What that gives you is a leading term of x to the 5th power. Now, because you have an odd exponent, that means your graph is going to be going in opposite directions, to the left and to the right. Since it is a positive and it's odd, that means it is going to go down to the left and it's going to go up to the right. Now the zeros of the polynomial we can get from right here. The 0 for this factor would be negative 3. The 0 for this factor would be positive 1. So negative 3 and positive 1. Now the multiplicity, we have 2 terms. We have an x plus 3 and we have an x minus 1. The x plus 3 has a multiplicity of 2 and the x minus 1 has a multiplicity of 3. All right, so how do we put this information onto a graph? We always start with your zeros. So we have zeros at negative 3 and positive 1. So put our points right there on the graph. Then you do your end behavior. Now, to the left of this point, our graph is going down. So that means we're going to be going down this direction. So I can just put a little arrow saying that we're going to be going down. To the right of our graph, we're going to be going up. So here's our furthest point to the right. So to the right of this point, our graph is going to be going up this way. So I'm just going to put an arrow showing what we're doing over here. So now at this 0, this is your first factor, which has a multiplicity of 2. You have an even exponent, and anytime you have an even exponent, that means that your graph is going to be tangent to the x-axis at that point. Okay, so once again, that goes back to this right here. When you have an even exponent, your graph is tangent to the x-axis. All right, so if you'll notice, this graph, it's not going to continue down forever at this point because we have another 0 that we have to go through. So at some point, this graph is going to have to turn and go back towards this other 0. We do not know how far down this graph goes. We're not really going to be concerned with that right now. All we know is that it's going to turn and go back towards this other 0 right here. Now, at this 0, the multiplicity is 3. When you have a 3, which is an odd number larger than 1, what that means is that your graph changes concavity. So it's going to change from concave down to concave up at that point. So it does not go straight through, it does a change in concavity. The only time it goes straight through is if your exponent is a 1. Okay. All right, so that is a sketch of what your graph of that polynomial would look like. All right, let's do another one. On this one, if you multiply x times x times x squared, your leading term, and you've got a negative in front of your parentheses right here, your leading term is going to be a negative x raised to the 4th power. Now, because you have x to the 4th power, that means our end behavior, it's going to go in the same direction. Because the leading term is also negative, it means that you're both going to go down to the left and to the right. So we're going to go down to the left and down to the right. All right, so next thing is pick out our zeros. Our zeros are the values that make each parenthesis 0. So -4 would make that parenthesis 0. -1 would make this parenthesis 0. And +2 would make this parenthesis 0. All right, so we have 3 factors. We have x plus 4, we have x plus 1, and we have x minus 2. Now, the x plus 4 has a multiplicity of 1 because the exponent is an understood 1 right here. X plus 1 also has a multiplicity of 1 because the exponent is a 1 right here. And then the x minus 2 has a multiplicity of 2. All right, so to graph, we start with your zeros. We have a 0 at -4, -1, and +2. Then you graph your end behavior. We're going down to the left. So to the left of this point, our graph is going to go down. So I'm just going to put a little arrow here, so indicating which direction we're going. And to the right, it's also going down. So to the right of the point over here, we're going to be going down forever. So I'm just going to put an arrow over here as well. So now what happens at each of these intersections? Well, at this one, it says the multiplicity is 1. Well, if you recall from our earlier notes, when the exponent is 1, your graph just goes straight through the x-axis, like this. Now, at some point, it does have to turn and come back down because we have another 0 that we have to go through right here. Well, at this 0, the multiplicity is also 1. So that means it's going to go straight through that point as well. Now this one over here has a multiplicity of 2. That means our graph is going to be tangent right here. Well, we can see that our graph is went through this point, but it also has to turn and go back towards our other 0 because we've got another 0 to go to. It cannot just go down forever. We've got to turn and then come back up to this point. And when we come to this point, it's going to be tangent, and then it goes down forever. And that is your sketch of what that graph would look like. All right, another example here. Leading term, you have a negative x to the third power times an x to the second power times another x to the second power. It's going to give you a total of negative x to the 7th power. Now, an odd power means you're going in opposite directions for your n behavior, and a negative in front tells you that you're going to be going up to the right, to the left, and you're going to go down to the right. Now your zeros, we have this one, that 0 is going to be a 7, this 0 is going to be a 4. We have another term here. The value that makes this 0 is 0. So anytime you have just an x right here, 0 is going to be that 0. So 0, 4, and 7 are the zeros. So we can go ahead and put our points on there. The multiplicity, x has a multiplicity of 3. X minus 4 has a multiplicity of 2. And then x minus 7 has a multiplicity of 2 as well. Now, over here we said it's going to go up to the left. So that means to the left of this point, our graph is going to go up. So let's go ahead and put an arrow here indicating our direction. To the right, our graph is going to go down. So after the last point on the right, our graph is going to be going down over here. All right, so I'm just going to put an arrow indicating that direction over here. Now at this value, the multiplicity was a 3, which means it does a change in concavity. Since we are coming from above the x-axis, it's going to change from being concave up to concave down. Now at the next 0, the multiplicity is 2, so it's going to be tangent. Now this graph right here is not just going to go down forever. It does have to turn and come back to this other 0. And when it does, it's going to be tangent. Now this other one also has a multiplicity of 2, which means it is going to be tangent at this point also. So our graph is going to have to turn, go back to this other 0, it's tangent, and then goes down forever. And that is your sketch of that graph. All right, and the last problem we have here, leading term. So we have an x to the first power, an x times an x squared times an x cubed times another x squared. It's going to give you 1, 3, 6, 8, x to the 8th power. Even exponent and a positive coefficient, which means we're going to go up to the left and up to the right. Zeros are going to be at 0 for this value. All right, so right here you're going to have a 0 that is 0, a 0 that's -5, a 0 that's -2, and a 0 that's +3. All right, so we have 0, -5, -2, +3. We can plot those points, -5, -2, 0, and +3. The multiplicity. The x has a multiplicity of 1. X plus 5 has a multiplicity of 2. X plus 2 has a multiplicity of 3. And then x minus 3 has a multiplicity of 2. All right, so the end behavior is up in both directions. So we know that we're going to go up this direction and up this direction. So at this 0, the multiplicity is 2, which means our graph is going to be tangent right here. Just going to touch it and then come back up. Now we do have to turn at some point and then come back down to this other 0. Now this 0, the multiplicity is 3, which means we're going to have a change in concavity right here. So it's going to be concave up and then concave down. So piecing it together would look like this. Now we've got another 0 right here, so we're going to have to turn and come back to this one. It has a multiplicity of 1, which means it's just going to go straight through there. And again, we're going to have to turn and then come back down to this 0. This 0, the multiplicity is 2. So it's going to be tangent to that one and then come back up.